This is Hounslow, Feltham, Stanwell, the homes surrounding Heathrow, one of the busiest airports on Earth. Nearly 1,300 flights a day, aircrafts passing overhead every 45 seconds during peak hours. And yet, people live here, sleep here, raise families here in old, semi-detached houses. How? The answer isn't £1 million soundproof bunkers. It's windows, just windows. My name is Eugene Korch. I practice and teach facade engineering, and today we will talk about acoustics in glass design. The job of building's facade is to act as filter, letting light and views through while keeping unwanted sound out. It sounds simple, but achieving this balance is one of the most challenging aspects of modern building design. When it comes to blocking sound, heavy construction has a natural advantage. Lightweight glazing has to work much harder to achieve the same result. The thick masonry walls of Victorian and Edwardian buildings were never designed with acoustics in mind, yet they perform remarkably well. How much harder the glass has to work, and what can we do about it? That is what we are covering today. Let me tell you more about Heathrow, one of the busiest airports in the world. 80 million passengers a year, over 450,000 flights annually. The homes around it face noise levels that will be unbearable. Aircrafts taking off and landing from early morning until nearly midnight. Since 1960s, the government has restricted night flights at Heathrow, but restrictions alone weren't enough. So in 1966, something remarkable happened. The first noise insulation grant scheme was introduced. The airport started paying to upgrade windows in nearby homes. This was a recognition that the acoustic performance of the building could be dramatically improved through targeted intervention. Not the walls, not the roofs, just windows. Why? Because the windows were the weak link, the path of least resistance for sound energy entering the building. That scheme has been running in various forms for nearly 60 years. The current program, launched in 2024, is investing in 20,000 homes over 8 years. Replacement windows, secondary glazing, and acoustic ventilation. Hundreds of millions of pounds spent on improving one building element. And here's the key insight. Look at the buildings around Heathrow. Victorian terraces with the solid brick walls, post-war semis with dense masonry construction, traditional buildings with thick, heavy envelopes. The walls don't need upgrading. They are already excellent at blocking sound. A typical Victorian external wall might be 350 to 450 millimeters thick, with a mass of over 800 kilograms per square meter. It is windows, and only the windows, that need attention. A traditional heavyweight wall blocks sound naturally. Dense materials like brick and concrete reflect and absorb sound energy instead of letting it pass through. The sheer mass of these walls means that sound waves struggle to set them vibrating. But the moment you cut a hole in that wall and fill it with glass, suddenly you've created the acoustic weak point of the entire building. Before we go any further, let's talk about how sound actually works. Sound is described using two key measurements. Decibels tell us how loud a sound is. Hertz tell us the pitch. Low frequency means deep bass. High frequency means treble. Here's an important thing about decibels. They don't work like normal numbers. The scale is designed to match how our ears actually perceive loudness. So the jump from 60 to 70 decibels feels about the same as the jump from 70 to 80. But in terms of actual sound energy, 80 decibels is 100 times more powerful than 60. Our ears compress that huge range into something manageable. But here's what makes acoustics fascinating. Human hearing isn't neutral. Research from Fletcher and Munson in the 1930s showed that we perceive sound subjectively depending on frequency. This is called the equal loudness counter. Our ears are most sensitive in the 2 to 5 kilohertz range, roughly where speech and crying babies sit. Evolution tuned our hearing for communication and danger. At the same decibel level, we hear mid-range frequencies as louder than bass or treble. This is why traffic noise, which is predominantly low frequency, can feel less intrusive than it actually is when measured. Understanding this relationship between decibels and hertz is essential. When we specify glass for acoustic performance, we are not just blocking sound, we are targeting specific frequencies that cause the most disturbance. There is a fundamental principle in acoustics called the mass law. It is beautifully simple. The heavier a barrier, the harder it is for the sound to pass through it. Sound waves carry energy. When a sound wave hits a barrier, it tries to make that barrier vibrate. The barrier then re-radiates that vibration as sound on the other side. The more massive the barrier, the more energy required to set it vibrating, and the less sound gets through. The mass law states that for each doubling of mass, you gain approximately 6 decibels of sound reduction. Double the weight, gain 6 decibels. Double it again, gain another 6. This relationship holds reasonably well across a wide frequency range. That for a 150 mm Victorian brick wall, it weighs around 800 kilograms per square meter. Dense, heavy, and extremely effective at blocking sound. And the standard 6 mm pane of glass? About 15 kilograms per square meter. The wall has over 50 times the mass, and the mass is the primary weapon against sound transmission. And this is why the traditional construction was acoustically excellent. Not because our ancestors understood acoustics, but because they built with heavy, dense materials out of structural necessity. Thick walls were needed to support the building. Those thick walls happen to be acoustically superb. Modern construction has changed this equation fundamentally. We separate the facade from the structure. We made walls thin and light. We embraced glass for its transparency and thermal performance, and as a result, building that can be thermally efficient, structurally sound, and aesthetically pleasing, but require careful engineering to achieve good acoustic performance. The mass our predecessors got for free is something we now have to design in deliberately. Now, the glass isn't helpless against sound. Modern glazing units are engineered systems with multiple components. But here's an important point. Double and triple glazed units didn't appear because of acoustics. They exist because of thermal performance, reducing U values and meeting energy efficiency requirements. Acoustics was never the primary driver. It is a secondary benefit we've learned to optimize for. This means that many standard configurations are thermally excellent but acoustically mediocre. Let's start with the glass itself. You'll encounter 3 types of monolithic glass on projects: annealed, heat-straightened, and fully toughened. Toughened glass is about 4 times stronger than annealed. Heat-strengthened sits in between, and they break very differently. Toughened shatters into small cubes, annealed and heat-strengthened into sharp shards. But acoustically, there's no difference whatsoever. Monolithic glass, whether it's annealed, heat-strengthened, or toughened, performs the same at equal thickness. The heat treatment changes the strength and breakage pattern, but not acoustic properties. The glass is still glass, same density, same acoustic behavior. However, the acoustic advantage comes from lamination. Laminated glass is essentially a sandwich, 2 or more panes bonded together with a polymer film, usually PVB, that is polyvinyl butyrol. Originally developed for cars' windscreens to prevent shattering on impact, laminated glass has acoustic benefits that weren't originally anticipated. The interlayer introduces damping into the system, reducing the amplitude of vibrations as they pass through. And there are specialist acoustic interlayers. They are softer, more pliable than standard PVB. Instead of transmitting sound from one pane to another, it converts that energy into tiny amount of heat through internal friction. The performance difference is substantial. Laminated glass with an acoustic interlayer consistently outperforms solid glass of equivalent total thickness, often by 3 to 5 decibels, a clearly perceptible improvement. Another trap to avoid: simply adding more glass doesn't always help. If you use panes of identical thickness, they resonate at the same frequency. When sound hits that frequency, both panes vibrate in sync, amplifying the problem rather than solving it. This is called coincidence. The solution is asymmetry. Different pane thicknesses mean different resonant frequencies. When one pane is at its weakest, the others compensate. The dips in performance occur at different frequencies, and the overall system maintains better performance. This is counterintuitive. A lighter asymmetric unit can outperform a heavier symmetric one. That is when design beats brute force. If you want to learn more about how glass types, glass cavities, gas infills, spaces, systems, and coatings affect acoustic performance, join our free webinar on this topic. The recording of the webinar and the course on acoustic glazing will be available to our members. Link in the description. When you see glazing specified for acoustic performance, you'll encounter a metric called RW, the Weighted Sound Reduction Index. It is a simple number representing average performance across standardized frequency range. The weighting is designed to reflect typical noise sources and human hearing sensitivity. The higher the number, the better the performance. Simple enough. But here's a trap that catches many designers. Real-world noise isn't neutral. It has character. It has frequency profile that varies depending on the source. Traffic is different from aircraft. Industrial machinery is different from speech. That is why acoustic ratings include adjustment terms. C is the correction for high-frequency noise, like speech and music. CTR is the correction for low-frequency noise, like urban traffic, aircraft, and heavy industry. The CTR value is almost always negative, meaning that the glazing performs worse against low-frequency noise than the RW alone suggests. A unit with RW42 and CTR -6 has an effective performance of only 36 decibels against traffic. This distinction matters enormously in real-world applications. At the start of any project in a noise-sensitive location, acoustic consultants conduct site surveys to determine the actual noise environment. They measure not just overall levels, but frequency characteristics. From that data, you get a specific target, RW plus C or RW plus CTR. And you need to hit that number precisely. Go below it and you will fail the requirements. Go above it and you may be spending money you didn't need to. Because in acoustics, every additional decibel of performance costs more than the last, and the relationship is exponential, not linear. The difference between RW35 and RW40 might require modest changes. The difference between RW40 and an RW45 might require specialist interlayers and dramatically thicker glass. Specify intelligently, match the solutions to the actual acoustic challenge. And those houses around Heathrow, they're still standing, still occupied, still livable. Families continue to raise children there, people continue to sleep peacefully. Because someone understood that the acoustic problem wasn't the walls, it was the windows. And because engineers developed solutions that could transform the acoustic performance of those windows. Modern architecture gives us extraordinary possibilities. Glass facades can deliver stunning aesthetics, excellent thermal performance, and, with the right engineering, outstanding acoustic protection. The physics hasn't changed since the Victorian era. Mass still matters. We also have discovered that asymmetry also matters, and the interlayers are helpful. What has changed is our understanding of how to manipulate these variables to achieve specific performance outcomes. Let me give you a concrete example of what a well-designed acoustic glazing unit looks like in practice. Consider a triple glazed unit for a residential project near a busy urban road. We want good acoustic performance, RW around 42 to 44, with a decent CTR correction, while maintaining reasonable thermal performance and cost. Here's one approach that applies all the principles we've discussed. Outer pane, laminated glass with PVB interlayer. First cavity, 16mm argon filled. Middle pane, 4mm monolithic glass. Second cavity, 12mm argon filled. Inner pane, thicker laminated glass with PVB interlayer. Notice the asymmetry at every level. The outer laminated pane is different thickness from the inner laminated pane. The cavities are different widths, 16 and 12. Even with each laminated pane, we could vary the individual glass thicknesses if needed. This unit combines three key principles: mass from the total glass thickness, lamination to provide damping through the acoustic interlayers, and asymmetry to avoid coincidence effect and resonance problems. The exact dimensions might change based on the specific project requirements, acoustic consultants' recommendations, and manufacturers' capabilities, but the underlying logic remains constant: mass, lamination, asymmetry. Those three words summarize the vast majority of acoustic glazing design.